Hello, good morning, good afternoon, and good night to everybody. So, welcome to my first class on real analysis. Actually, I am discussing about the basic concepts of real analysis in this lecture. And this topic will cover actually what is the real analysis course and the concepts of sets. Actually, the Cantor, who is the founder of set theory. Then we define what is field and the properties of real number in a space, properties of Bessel, supremum and infimum in real analysis, neighborhood and limiting points, sequence and series, Heine-Borel theorem, Bolzano-Wierstrass theorem, and Cantor set theorem. So first of all, what is real analysis? Actually, real analysis is a branch of mathematics that studies how real numbers, sequence, and series and real functions of real numbers behave. Secondly, the important topics which are covered under real analysis are real number system, sequence and series, limits and continuity, integration, differentiation, Riemann integration, and convergence, and compactness, and so on in both single variable functions of real numbers and multivariable functions of real numbers. Now, the real analysis is a discipline of mathematics that was developed to define the study of real numbers and real valued functions, as well as investigate the essential concepts such as limit and continuity and uniform continuity. These concepts underpin calculus and its applications. Real analysis has become an incredible resource in a wide range of application in modern mathematical analysis. First of all, what is set? A set is a collection of objects called elements or numbers or anything that is well defined. The empty set denoted by the null is the set with no elements. There are a few symbols that are super helpful to know as a shorthand and we'll use throughout the lecture. And S is the set. A belongs to S means A is an element of S, and this means existence means there exist. And A doesn't belongs to S means A is not an element of S, and existence, there exists a unique for all, and this will be used as defined. And this implies, and this means if and only if. So first of all, what is the set relations? We want to relate different sets, thus we get the following notation and definition. And A set A is a subset of B, can be written as like this. And similarly, the sets will be equal if and only if this. A set A is a proper subset of B will be written as like this. Okay, but the number of elements and number of elements B will be not equal if A is the subset of B, not proper subset. So on the way we can describe the set by set building notation X, the element of A such that P of X. Okay, this is the there are different kinds of sets we can define. The set of natural number 1, 2, 3, 4, the set of integers z 0, 1, minus 1, 2, the set of rational numbers q, and the set of real numbers, of course, like r. Okay, so it follows that natural number are the subset of real numbers, and the real numbers are the subsets of rational numbers, and rational numbers are the subset of real number. This is the integer, that is the integer. So natural number always subset to the integer, and integer always subset to the rational numbers, and rational numbers and irrational numbers are also the subset of real numbers. Now, function of a set in a Cantor's theory can be denoted by like this. If A and B are sets, a function f from A to B is mapping that assigns each element of x, element of A, to a unique element in B denoted by f of x, and let f is a function A to B. Then there are two conditions. One, C will be the subset of A. We define f of C equals to this. And if D equals to subset of B, then we define f inverse D, x belongs to A, such that f of x belongs to B. For an example, considering the following mapping from f is a function from A to B. A is the subset with elements A 1, 2, 3, 4, and B is the subset of elements with elements A, B. So if we map to this, we obviously see that there is a mapping from A to B, and the inverse of set B will be 3, 4. So there are different types of function of a sets. F is injective or 1, 1 or 1, 1 if f of x1 equals to f of x2. That means which implies x1 equals to x2. F is surjective. Surjective means onto function. If all the image elements of f will be equal to the set elements of set B. So f is bijective if it follows the two conditions, injective and surjective. That means if the set of function is 1, 1 and on 2, then it is called bijective. If a function f is a from A to B bijective, then with f inverse, inverse function will be exist from B to A is the function which assigns y belongs to B to the unique x belongs to A such that f of x equals to y. So in that case, we can define the inverse function of set like this. So what is cardinality? Cantor answered this question in 1800, stating that two sets have the same size when you can pair each elements in one set with unique element of the other. That means, first of all, what is the cardinality? We state that two sets A and B have the same cardinality if there exists a bisection function from A to B. That means bisection means what? Actually, it is 1, 1 and on. So this new concept comes, some new notations. So cardinal of set A equals to cardinal of set B if and only if A and B have the same cardinality. And if the cardinal of A equals to n, and if cardinal A equals to 1, 2, dot, dot, n, then if this in this way, then A is finite. If cardinal of L is equals to B, if there exists an injection, f is a function from A to B. Injection means what? Actually, 1, 1 function. Okay. And if the cardinal of A less than cardinal B, then we if cardinal of A less equal to B, in that case, cardinal of A is not equal to cardinal of B. So there is actually an inequality Cantor, Schroeder, Bernstein. If cardinal of A is equal to B and B cardinal of B is equal to cardinal of A, then cardinal of A equals to cardinal of B. So in that case, we can use this example. If cardinal A is the cardinal of natural number, then A is countably infinite. If A is finite or countably infinite, we say A is countable. Otherwise, we say A is uncountable. So for example, there are a few key theorems that can prove that with the new concept. Actually, twice n, that means or even number such that n belongs to n equals to what will be natural number. And similarly, odd numbers will be also natural number. And if x is the element of rational number, x greater than 0, then it's also natural number. So we can prove it easily. Now, a Cantor's theorem. If A is a set, then cardinal of the set A less equals to the cardinal of power set of. Okay. So therefore, a natural number less than cardinal of power set of A less than cardinal of power set A of natural number less than dot dot. Here there are an infinite number of infinite sets. Now we can prove this Cantor theorem. Define the function f is a function from A to power set of A by f of x equals to x. Okay. Then f is 1 as the set x equals to set y, which implies that x equals to y. Thus, cardinal of L is equals to power set of cardinal of power set A. To finish the proof, now all we need to show that it is cardinal of A not equal to cardinal of power set of A. We will do so through the contradiction. Suppose that cardinal of A is equal to cardinal of power set of A. Then there exists a surjective function z such that A to power set of A. Let B equals P and be defined as x belongs to A such that x is not element of Gx, which is subset of power set of A. Since this is surjective, you must know surjective means what? There exists AB belongs to A and GB equals to B. Then there are two cases. One is if B belongs to B, small b belongs to capital B. In this case, B doesn't belongs to GB, which is equal to B, which implies B is not equal to B. If B is not element of capital B, if this is in the case, then B doesn't belongs to GB equals to B. In that case, small b belongs to capital B. Now, otherwise, we obtain the contradiction. That means is not surjective. So the cardinal of A is not equal to cardinal of power set of A. So this is the proof for Cantor's theorem. Okay, now order of sets and fields. First of all, what is ordered set? An ordered set is a set S with a relation less than called an ordering such that for all x, y belongs to S, either x less than y less than x, or x equals to y. So number two, if x less than y and y less than z, then x less than z. Here are a few examples and one non-example here. If integer z is an ordered set, then with the relation that m greater than n, if and only if m minus n also belongs to n. Q is rational number Q is an ordered set with the relation p greater than q if and only if existence mn belongs to natural number such that p minus q also m by n. If we take the order of rational number to rational number, then with relation q are greater than st, which implies q greater than s and s or q equals to s and r greater than t. Consider the set power set of natural number. Let AB belongs to power set of natural number. Let A is the less than B if A is the subset of B. This is not an order set. It does not satisfy the first property of an order set. So you have to remember that the properties. This is the two properties of ordered set. Now bounded above or bounded below. Let S be an ordered set and is the subset of S. Then if there exists a B belongs to S such that X less equal to B for all X belongs to E, then E is bounded. Okay, then E is bounded because B is the less equal to with less equal to sign. Bounded above, and B is an bigger element of E. If existence C belongs to S such that X greater equal to C, then C is the less number or equal to X for all X belongs to, then E is bounded below. So from here, there are two very important definitions of real analysis. We said that B0 is the least upper bound or supremum of E. Now, what will be the supremum and what will be the infimum. We'll discuss it in later. Now, what will be the least upper bound or supremum? An order set S has the least upper bound property if every open set E, which is subset of S, which is non-empty and bounded above, has a supremum in S. For example, one example such that all negative natural number, negative integer, -1, -2, -3, then then is the subset of S bounded above if and only if minus is the subset of N is bounded value. So in that case, we can say that uh, minus E has a least element x belongs to minus E. Thus minus x equals to supremum of E. So the supremum and so the lower upper bound or least upper bound or supremum can be defined as lower upper bound of a set. Suppose S is an ordered set and is the subset of S. And if there exists a beta belongs to S such that x greater or equal to beta for every x belongs to E, then we say that E is bounded value and call beta is a lower bound of E. For example, capital E equals to -9, -2, half, and 6. From this set, -9 is the actually the number which is less than other elements of E. So -9 is the lower bound. Similarly, from the interval open interval -1 infinity and is the subset of real number is bounded value. Since there exists say beta equals to -2, which is belongs to real number such that x greater or equal to beta for all x belongs to A and beta equals to -2 is lower bound of E. So you can describe it in real number line and natural number has no any upper bound and 1 or any number less than 1 is a lower bound of natural number. Now what will be the bounded set? Suppose S is an ordered set, E is the subset of S, then E is called bounded if it is a bounded above or bounded value. For example, E equals to -1, 0, 3, 8, 7. Here E is bounded since it is bounded above and bounded value. Unbounded set what will be? If E is not bounded, then it is called unbounded. Integer is not bounded since it's neither bounded above nor bounded below. Now what will be the least upper bound or supremum? So let S be an ordered set is the subset of S and is bounded above, then an element alpha belongs to S is called a least upper bound or supremum of E if it has the following two properties. Alpha is an upper bound of E and no upper bound of E less than alpha, which is denoted by alpha equals to least upper bound of E or alpha equals to supremum of E. So alpha equals to M. For example, let E equals to 1, 2, 3, 8. Here lowest least upper bound of E will be supremum of E and which is equal to E. Similarly, from F, 9 is the supremum. And in Z, actually, G has no least upper bound or supremum. So supremum Z does not exist here. In the set A's also, least upper bound or supremum A's equals to 1. And in I set, here least upper bound what will be? Is a series is 5, 1. Now greatest lower bound, that means infimum. Suppose S is an ordered set, E is the subset of S and E is bounded value, then an element alpha belongs to S is called the greatest lower bound or infimum if E satisfies the following two properties. So alpha is a lower bound of E. No lower bound of E is greater than alpha, which is denoted by alpha equals to greatest lower bound of E or alpha equals to infimum of E. Now, for example, the set E with the elements 3, 5, 6, 8, where greatest lower bound of E or infimum E equals to what 3. and here minus 2, minus 2, minus 3, minus 4. But in this set, greatest lower bound of V, the infimum of V does not exist. Similarly, from Z and A's, we get infimum 3 by 4 and 0, etc. So this is actually basic concepts of analysis. Now, what is the maximum element? Maximum element. Suppose S in order set is the subset of S and is bounded above, then an element alpha belongs to S is called maximum element or the largest element of E. If alpha belongs to E and lowest upper bound of E or supremum equals to what will be alpha. It is denoted by alpha equals to maximum. From the set E, maximum equals to 4 and E maximum equals to supremum of E1, but maximum does not exist. Okay, because 1 doesn't belongs to F. Similarly, Z equals to, from this set, least upper bound or supremum or maximum Z equals to minus 1. And in the set, supremum A's does not exist and is therefore maximum also does not exist. Similarly, minimum element or smallest element. Suppose S is an ordered set, E is the subset of S and is bounded value, then alpha belongs to S is called minimum element or the smallest element of E. If alpha belongs to S, E and alpha equals to greatest lower bound or infimum. Now let E is the set with elements 4, 5, 8, 11, 15. Their greatest lower bound or minimum of E will be 4. Similarly, from the set F, we observe that greatest lower bound actually 0, but minimum F does not exist. So, and the integer has no greatest lower bound and also no least upper bound, also no minimum element. Infimum of natural number equals to minimum element of natural number is 1, but supremum of natural number does not exist. Therefore, maximum of natural number does not exist. You have to remember this. Show that the supremum of a subset of R, if there exists unique, suppose S is an ordered set, is the subset of S and is bounded above, then supremum of E equals to alpha, then there exists alpha is unique. If possible, let beta be the another supremum of P. So therefore, supremum of P equals to beta. Then by definition, alpha is an upper bound of E and beta is an upper bound of also P. If supremum E equals to alpha, least upper bound, then we have alpha as equals to P. And again, if supremum E equals to beta, then in that case, beta equals to as equal to alpha. So from this both inequality, we observe that alpha equals to beta. So supremum E has unique elements. Similarly, uniqueness of infimum, we can easily derive the uniqueness theorem. Now we define what is the actual field. A set F is a field if it has two operations. One is addition, another is multiplication with the following 10 properties. So A1, A2, A3, A4, A5 is the properties for addition, and M1, M2, M3, M4, M5 also properties for multiplication. So if the any set satisfies these 10 properties, and it will be called field. So first, closure law, if xy belongs to F, then x plus y also will be belongs to element of F. So commutativity, associativity, existence of an identity element for all x and existence y belongs to F, there x plus y equals to 0, with and y equals to minus. So inverse element. Okay, if xy belongs to F, then x into y equals to closure law for multiplication. Similarly, commutative law for multiplication, associativity law for multiplication, existence identity element 1 belongs to F such that 1 into x equals to x and equals to x into 1 for all x belongs to F. So 1 is the identity element, and for all x belongs to F, if we take the 0 element existence x inverse such that x into x inverse equals to 1, that means multiplicative inverse exists. Similarly, distributive law, it's a combined law of addition and multiplication. So x plus y into z equals to xz plus yz, where xyz belongs to F. So actually, this is the definition of field or properties of field. So there are two examples of field. One is Z2 equals to 0, 1, where the 1 plus 1 equals to 0 by using modulus. Then Z3 0, 1, 2, 3, where C defined as a plus B mod 3. In other words, 2 plus 1 equals to 3 also 0, and 2 into 2 equals to 4 equals to 3 plus 1 can be written as 1 mod 3. So this is the two examples of field. So now we also defined what is the ordered field. This is the actually definition for ordered field. And rational number is an ordered field. You have to remember this. And a field F is an ordered field if F is also ordered set with the ordering less or equal to or greater than. For all x, y, z belongs to F, x less than y imply x plus z equals to y plus z. Number two, if x greater than 0 and y greater than 0, then we also can be written as xy greater than 0. If x greater than 3, we can say x is positive, and if x greater or equal to 0, we can say x is non-negative. So, for example, Q is an ordered field. So, now what is the Archimedean property? For all x, y belongs to R, x less than y, there exists and R belongs to R such that R lies between x and y. That means R can be taken as average of x plus y. So in that case, Archimedean property can be extended of real numbers. Now some properties of real numbers. Actually, we will state some important consequence of the field properties in previous slide of real numbers. Similarly, we can define the properties of real numbers. There exists a unique identity element for addition in R. There exists a unique additive inverse also in R. A plus B equals to A plus C equals to B. Then we can write B equals to C. A plus B equals to A, then we can write B equals to Y. It is from by actually cancellation law. So this is actually important properties of real number. If A is not equal to 0, then AB, if AB equals to AC, then we can write B equals to C by cancellation, loss of multiplication. If A is not equal to 0 and AB equals to A, then we can write B equals to 1. Similarly, actually, there are 22 properties of real numbers. 1 by AB can be written as 1 by A and 1 by B, where A is not equal to 0 and B is not equal to 0. If A is equal to 0 and B equals to 0, it cannot be possible in real field. So integral power of real number. Let A is the elements of real number. If n is a positive integer, we can define A to the power n equals to n to n to n factors. So in particular, we can write A to the power n equals to A. Then we can define A to the power 0 equals to 1. So now we also discussed the ordered axioms. This is the order for any two real numbers. It is known as the laws of trichotomy and laws of for addition, laws for multiplication also exist in ordered field. This is actually some more definitions of ordered field. So now what will be the finite sets and infinite sets? A set is said to be finite if it consists of a specific number of distinct elements. That is, if in counting the distinct number of the set, the counting process can come to an end. Okay. Suppose A is the set of the days of the week. So A is finite and B is cannot be finished. So this is the set of odd natural numbers and B is finite. So the set of natural number, a subset S of real number is called inductive set if one belongs to S and P belong element of S implies P plus 1 also element of S. For example, real number itself is an inductive set. So rational numbers, we also can define irrational number also can be defined. And we can also prove root over 2 is an irrational numbers. It's very easy for you. Now, what will be the intervals? A subset S of R is called the interval if AB belongs to S and X belongs to real number and X lies between AB, then X will be the element of S. If AB are any two real numbers such that A is equal to B, then the set can be defined as with open interval. It's called also open interval. Similarly, we can also define S with closed interval, and this is called semi-closed, and this is the semi-closed and semi-open. And finite and infinite subset. A subset S of real number is said to be finite if either it is empty or there exists a one-to-one mapping from the set of natural number into the set S for some natural number n. A set S of R which is not finite is called infinite set. The sets natural number, integers, rational number, real numbers are infinite. And the set E pi root over 2 is a finite set because from the set of natural number onto the set, this may one-to-one mapping exists. So on such mapping, 1 map to E, 2 map to pi, and 3 map to root over 2. This is why it is a finite set. Number 3 example is also finite sets, and number 4 also finite sets. Now what will be the absolute value or modulus of a real number? Actually, modulus of real number can be written as like this: x if x greater or equal to 0 and minus x if x less than 0. So you can find minus 5 equals to actually 5, but minus 5 is not equal to 5. We have to remember this. This is the actually properties of modulus of or absolute value of x in real number, and this is also true. So the Archimedean property, Archimedean properties of real numbers, the order completeness property of real number has important consequences. The most important of them is the following Archimedean property of real number. So let A be any real number and B any positive real number, then there exists a positive integer n such that n be greater than A. So we can prove it easily. If A is equal to 0, the theorem obviously, because then it for every positive integer n, we have n be greater than A. Note that n greater than 0, b greater than 0 implies n be greater than 0. So if L is equal to 0, then it means negative, then we have n be greater than A. So now let A will be the positive. In this case, we assume that there exists no positive integer n such that n be greater than A. So we have n be less equal to A for all n belongs to natural number. It means that A is an upper bound of the non-empty subset S of real number given by S equals to B, twice B, thrice B, 4B, etc. So it can be written as NB such that n belongs to natural number. By the completeness property of R, S must have the supremum or least upper greatest lower bound. Says S, then NB less equal to S for all n belongs to natural number. So n plus 1 B less equals to S, inequality property for all n belongs to n. Because we must know n belongs to n implies n plus 1 also belongs to natural number. In that case, NB plus B less equals to S for all n natural number and NB less equal to S minus B for all n natural number. So S minus B is an upper bound of the set S. Since B greater than 0, therefore S minus B less than S. Okay. This is why it means that we have an upper bound for S which is less than the supremum S, small s of capital S order set. But this contradicts the definition of the supremum. Hence, our initial assumption is wrong. So there must exist some positive integer n such that n be greater than a. Actually, this is the proof of Archimedean property. Now, another important axiom, that kind Cantor axiom, to every real number, there corresponds a unique point on a directed line, and conversely, to every point on a directed line, there corresponds a unique real numbers. So this is called the axiom of that kind Cantor. And the real number is called a point of the real line also. Now, the denseness property of real number system. So between any two distinct real numbers, there always lies a rational number, and therefore infinitely many rational numbers. Proof: let A be any two distinct real numbers. That means A less than B. That means A is greater than B. So B minus A also positive. Since B minus A is positive, therefore the Archimedean property, by the Archimedean properties, you can write n B minus A greater than 1. That is n be greater than n plus 1. And also there exists a unique integer m such that m minus 1 less equals to na less than m. That means na lies between m and m minus 1. So that na plus 1 greater or equal to m greater than na. From equation 1 and 2, we observe that actually n be greater than na plus 1 greater or equal to m greater than na, which gives na, that means m lies between na and mb. So dividing by n in both sets, a less than m by n less than b. Here m and n are integers, n is not equal to 0. Therefore, m by n is a rational number. So if we denote m by n rational number r, then this rational number lies between a and b. And thus there exists a rational number r lying between a and b. Now repeating the above arguments for a and r and b, we get rational number says R1, R2. R1 lies between A and R, and R2 also lies between R and B. Combining this, we get A less than R1, less than R, less than R2, less than B. So continuing in this process, we get infinitely many rational numbers between A, any two distinct real numbers, and B. So this is called actually denseness property of real number systems. Using similar process, we can also prove the theorem between any two distinct real numbers. There always lies an irrational number, and therefore infinitely many irrational numbers. So using the similar concepts, we also prove this result here. We also can prove between any two distinct real numbers, there lies an infinite number of real numbers also. Now, another important concept, neighborhood of a point. A subset n, natural number of real number, is said to be neighborhood of a point P belongs to R if there exists a real number epsilon greater than 0 such that existence P minus epsilon, P plus epsilon, which is the subset of natural number. Since P belongs to this interval, closed, open closed, and P minus epsilon, P plus epsilon, which is the subset of natural number. Therefore, if n is a neighborhood of P, we must have P belongs to natural number. Now, natural number is the subset of real number, is a neighborhood of a point P belongs to. There is an open interval containing n whose center is the point P. For example, n is the closed interval, n is the n to be the closed interval, and n is the neighborhood of a point 4 belongs to this interval. So because epsilon equals to 1 by 4 is a positive real number such that we can define according to the definition. Now we can define a subset N of R is a neighborhood of a point P if and only if there exists an open interval AB containing P continued in natural number. That is, if and only if there exists an open interval such that P belongs to this. So we can define the neighborhood in so the neighborhoods at a non-empty subset N of R is called a neighborhood of a point x naught belongs to R if there exists an open interval I such that x naught belongs to I, which is the subset of natural number. Now what will be the epsilon neighborhood of x naught? Let x naught be a real number of open interval AB, then x naught lies between AB. It always possible to find a small number epsilon greater than 0, which is very small, such that the open interval x naught minus epsilon, x naught plus epsilon will be contained in open interval AB. That means subset of AB. So hence this is the neighborhood of x naught, which is belongs to open interval AB. This neighborhood of x naught is called epsilon neighborhood of x naught and is denoted by n epsilon and x naught epsilon. Epsilon is the actual center and epsilon is the radius of a ball. So epsilon neighborhood of x naught can be written as a with the inequality. Now what will be the deleted neighborhood of x naught? If from the neighborhood of a point, the point itself is excluded, then we get the deleted neighborhood of a point. If n is a neighborhood of x naught, then the set n minus the element x naught is the deleted neighborhood of x naught. The set x naught minus epsilon, x naught plus epsilon open interval minus excluding x naught is defined as the deleted symmetric neighborhood of a point x naught with radius epsilon. So deleted neighborhood can be written as a open ball like this. Okay, now another important concept of adherent point or limit points or cluster points of a set. So what will be the adherent point? A point P belongs to real number is said to be an adherent point of a set A, which is subset of real number, if every neighborhood of P contains a point of A. The set of all adherent points of A is called the adherence of A and it's denoted by ADS of A. From the above definition, it is obviously that every point of A is an adherent point of A. That means A is the subset of adherent of A. Now, what will be the limit point or cluster point? A point P belongs to R is said to be a limit point or an accumulation point or a cluster point or a condensation point. Same words of A set capital A, which is a subset of real number. If every neighborhood of P contains a point of A distinct from P. You have to remember this. Different from P. Thus, P will be the limit point of A if and only if for each epsilon greater than 0, there an open interval P minus epsilon and P plus epsilon contains a point of A other than P. Symbolically, a point P is the subset element of R will be the limit point of the subset A of R if and only if N is the intersection A, but you have to take the difference or delete the P element. If we delete the P element, then the number of elements will be non-empty. So for every neighborhood of N of P. So in that case, we can define N minus P, which is the intersection to A, which is non-empty for every neighborhood of P. And intersection A minus P also non-empty for every neighborhood of P. In that case, the open interval will be intersection with A minus P element also non-empty for every epsilon greater than 0. So from the definition of a limit point of an adherent point of a set A, which is subset R, it is obvious that every limit point of A is also adherent point of A, but the converse is not true always. For example, and 1 is the adherent point of this series, but it is not a limit point of this set. A limit point of a set may or may not belongs to A. Now, closed set. What is the definition of closed set? A set A is the subset of R is said to be closed set if it contains all its limit points. So you have to remember that every limit points will be contained in a set. Then those types of set is called closed set. So isolated points. A point A belongs to A is said to be an isolated point of A if it is not a limit point of A. That is, if there exists a neighborhood of A which contains no points of A other than A itself. A set A is called a discrete set if all points are isolated points. For example, of the set A, 1/2, 1/3, 1/4, etc. It's isolated points, and so it is a also discrete set. Now, what will be the perfect set? A subset A of a real number is said to be dense in itself if it possesses no isolated points, or every point of A is a limit points of A. Furthermore, a set is called perfect set if it is dense in itself, if it contains all its limit points. So there are different theorems on limit points. We'll discuss in our later class. Okay, now we'll discuss a very important theorem on a limit point of real numbers, Bolzano-Wierstrass theorem. Every infinite bounded set of real number has a limit point. Okay, proof: let S be an infinite bounded set of real numbers, and let S and K be its minimum, infimum, and supremum respectively. Note that both S, K exist by order completeness property of real numbers we have discussed in earlier. Let us define a set A as follows. Capital A. A real number X belongs to a capital S if and only if it exceeds at most a finite number of member of S, which is infinite bounded set. That is, capital A can be written as a X such that X will be the element of real number, and the number of elements of S which are less than X is finite. Since S equals to infimum of S, therefore X greater or equal to S for all X belongs to S. Therefore, X exceeds no member of S. That means S cannot be greater than the element of S. So by our definition, capital A is definition of capital A is we can write small a belongs to A, thus capital A is non-empty. Also, no member of greater than K is in A. Therefore, let Y greater than K, which is equals to supremum of S. Then X less than Y for all X belongs to S. Therefore, Y exceeds all the member of S which are infinite because S is an infinite set. Therefore, if Y greater than K, then by our definition of capital A, Y cannot be element of A. The set A is bounded above with K as an upper bound. That means supremum. So therefore, A is a non-empty subset of real number bounded above by K. Hence, by order completeness property, A must be a supremum of real number. Let supremum of S equals to P. We shall show that P is a limit point of S. Now let us consider epsilon greater than 0, which is very small. Since supremum S equals to P, therefore P minus epsilon cannot be an upper bound of S. Therefore, there exists X belongs to S such that X greater than P minus epsilon, where P minus epsilon is less than X. Therefore, X belongs to S. Therefore, it exceeds at most finite number of members of S. And consequently, P minus epsilon also exceeds at most finite number of member of S. In that case, again, since P is equal to supremum of S and P plus epsilon cannot belongs to S, so P plus epsilon exceeds or cross an infinite number of members of S. Therefore, P minus epsilon exceeds only a finite number of S, and P plus epsilon exceeds an infinite number of member of S. It means that the neighborhood of open interval P minus epsilon P plus epsilon of P contains infinitely many points of S. Since epsilon is arbitrary, therefore a very epsilon neighborhood of P, therefore every epsilon neighborhood of P contains infinitely many points of S, which are the limit points. Therefore, the P supremum of A can be said that it is a limit point of S. Therefore, we have proved that actually every infinite bounded set of real number has a limit point. This is the actually proof of Bolzano-Wierstrass theorem. We have to remark that the condition in the above theorem are only sufficient conditions for a set S to have a limit point. These conditions are not necessary for a set S to have a limit point. Even an infinite unbounded set may have a limit point. For example, the set Q, rational number of a number, is unbounded and still it has limit points. So we know that every real number is a limit point of the set Q. So this is the actually very important theorem of real analysis. Now what will be the interior of a set? Interior of a set. Let S be a subset of R. A point P belongs to S is said to be an interior of S if there exists a neighborhood in open interval P minus epsilon P plus epsilon of P which is entirely contained in S. If there exists epsilon greater than 0 such that the open interval will contained in S. So interior of a set. If S is a subset of R, then the set of all interior points of S is called the interior of S and is denoted by S naught or interior of S. Obviously, interior of S is the subset of S. You have to remember this. Now, what will be the open set? Let S be a subset of R, then S is said to be an open if every point of S is an interior point of S. The following two characterization of an open set immediately follow from the definition. A set S is open if and only if interior of S equals to the S. So a set S is open if and only if it contains a neighborhood of each of its points. Now another important property is closure of a set. Let A be any subset of R, then the closure of A is defined as the smallest closed set containing A and is denoted by closure of A bar. The following two results are quite obvious. A bar or closure of a set is the intersection of the family of all closed sets containing A. A is closed if and only if closure of A equals to the set A itself. Now, what will be the sequence? If S is any non-empty set, a function whose domain is the natural number n and whose range is a subset of S is called a sequence in S. In other words, a sequence in S is a rule which assigns to each natural number to a unique element of S. S will be the element of real number. A real sequence, a sequence whose range is a subset of real number is called real sequence of real numbers. So there are different examples listing the order, the first few elements of a sequence, still the writing down the, for example, 1, 8, 27, 64 is the sequence whose nth term is n cube. During the sequence of formula nth term, we can also write this. We can write also recursion formula. For example, 1 by n is the sequence, 1 half, 1 by 3, etc. And n by n plus 1 also sequence of this. And minus 1 to the power n divided by n is also sequence. Range of sequence. The set of all discrete terms of a sequence is called its range. The range of sequence Sn will be the set S1, S2, dot, dot, etc. the range of sequence minus 1 to the power n will be minus 1 and 1, which is a finite set. Similarly, the range of sequence 1 by n will be 1 by n such that n will be the natural number, element of natural number, but the element of natural number is infinite. So the range of sequence of this sequence will be also infinite. Now constant sequence, what will be? A sequence Sn defined by Sn equals to A for all n belongs to n is called a constant sequence. That means the range value, image value will be same. Now we'll discuss the second part of this lecture. Actually, basic concepts of sequence and series. In earlier we discussed Bolzano-Wierstrass theorem. Now I will discuss about the basic concepts of Heine-Borel theorem. So before discussing this theorem, we have to discuss some basic concepts connecting to them. So first of all, what's the norm and distance? Actually, in real number or in a space of real number is the set of all n vectors such that x equals to x1, x2 dot dot xn, where each xi is a real number for I equals to 1 to up to n. So the Euclidean norm of a vector x belongs to Rn is denoted by the double dash x in both sets and defined by the norm of x equals to bracket x1 whole square plus x2 whole square plus dot dot plus xn whole square to the power half. So the main properties of norm, the norm will be non-negative, and if norm is 0, then if and only if x equals to 0. And this is the another second properties, and norm of lambda x equals to norm of lambda into norm of x, absolute modulus of lambda into norm of x. And this is the triangle inequality, norm of x plus y less equal to the individual norm of them, x, norm x of x plus norm of y, and norm of xy less equal to norm of x into norm of y, Cauchy-Schwarz inequality also. So what is the metric or metric space? For xy belongs to Rn, the distance between x and y denoted by dxy is dxy equals to norm of x minus y. So the distance between x and y is called the actually metric or distance. Note that if the distance of x0 is the actually norm of x, so the norm of x can be interpreted as the distance from x to the 0 vector. Now properties of distance and distance function dxy is non-negative and dxy is equal to 0 if and only if x equals to y. And the commutative property of dxy equals to dyx. And this is the triangular inequality dxz less equal to dxy plus dyz. So this is the actually basic properties of metric space. Now, what is the sequence? A sequence of a real number can be assigned of a real number to each number. The notation can be xn, third bracket, means the sequence of whose now what will be the limits of sequence? So let x1, x2 dot dot xn be a sequence of real numbers. A real number x is called the limit of sequence xn. If given any real number epsilon greater than 0, there is a positive integer n such that the distance, the modulus of xn minus x less than epsilon whenever small n greater equal to capital N. If the sequence has limit, we call the sequence is convergent. Otherwise, it will be divergent. So if x is a limit of a sequence, x is a limit of a sequence xn, we said that the sequence converges to x and can be written as like this. Now, this is the examples of, there are 3 sequence of example. This is the, now what is the limit, what is the limit point or accumulation point or a cluster point, same words. If xn is a sequence of real numbers and x is a real number, we say that x is a limit point or accumulation point or cluster point of the sequence. If the given a real number epsilon greater than 0, there are infinitely many elements xn of the sequence such that xn minus x modulus modulus of xn minus x will be less than epsilon. A limit is a special case of a limit point. A sequence can have a number of different limit points, but only one limit. So this is the actually basic definition of limit point. Now, a sequence Rn is an assignment of a vector Rn to each natural number. Now, what is open ball? Let x vector belongs to Rn and epsilon be a positive number, which is very small. An open ball with center x and radius epsilon in Rn can be written as b epsilon x bar equals to x belongs to Rn and norm of x minus x bar less than epsilon. Intuitively, a vector y in Rn is close to x bar if y is in some open ball of x bar with radius epsilon. For a small but positive epsilon, the smaller epsilon is closer to y is to x bar. So a sequence vector of vector Rn is said to be converse of the vector if the given real number epsilon greater than 0, there is a positive integer n such that xn minus x norm less than epsilon whenever small n greater than 0. In that case, the xn will be the element of open ball of x with epsilon radius for all small n greater than capital N. A vector x is called a limit of the sequence. Now, what will be the subsequence? Let xn be a sequence of vectors in Rn and nr be a strictly increasing sequence of the natural numbers. Then the sequence xnr is called subsequence of the sequence. Example, consider this is the subsequence and this is another example. If a sequence has a limit point, it may none have no limit. So, however, if a sequence has a limit point, then there exists a subsequence that converges to the limit point. Now, what will be the open set? A set S is the subset of Rn is open for every x belongs to S. There exists an open ball with center x and radius epsilon greater than 0 in R, which is completely contained in S. That is, x is the element of S implies there is an epsilon greater than 0 such that the whole ball with center x and radius epsilon will contained in S. In that case, the set is called open set. If x belongs to Rn, an open set as containing x is called an open neighborhood of x. Thus, an open ball with center x and radius epsilon greater than 0 in Rn is an open neighborhood of x. The word open has a connotation of a no boundary. From any point of the set, one can always move a little distance in any direction and still be in the set. Consequently, open sets cannot contain their boundary points. You have to remember this. This is very important properties of open sets. Open sets cannot their boundary points. For example, use the definition to show the 1, 2 is the open is an open set. So now what will be the interior of a set? Let S be a subset of Rn. And the interior of S denoted by int S, the union of all open sets contained in S. So by the definition of interior of set considered as the largest open set which is contained in the given set. The interior of an open set S is that set S itself. Now what will be the closed set? A set S is the subset of Rn is closed if whenever xn is a sequence of point of S that is converse in Rn. So we have limit and tends to infinity xn will be the element of S. Thus, if X is a given point and if there are points in a closed set S which are arbitrarily close to X, then X must be in S2. Consequently, a closed set must contain all its boundary points. This is another properties of closed set, just the opposite of the situation with the open sets. For example, the set S, x1, x2 belongs to R square, where x1 and x2 are non-negative. In that case, this circle with radius 1 and center will be 0, 0 is the closed set in R. Now, complement of a set, you must know complement of a set, so which is not contained in S. Now, what is the compact set? First of all, what's the bounded set? A set S is the subset of Rn. Will be bounded if it is contained in some open ball in Rn. So now compact set, a set S is the subset of Rn is compact if and only if it is both closed and bounded. So the set will be both closed and bounded. For example, number 1, 2, 3 are the example of compact set. First one is compact set, but the second one is not compact set. It is not closed. This is why this is the closed and open, closed open interval and closed open interval. This is why not compact set. S3 is also not a compact set, as in no bounded, because 0 less this is not bounded. 0 less equal to x2. This is not bounded set. So this is the example of compact sets. And we have discussed this proof. Now I'll try to understand the now Heine-Borel theorem. Let F be a closed and bounded set of real numbers. Then every open cobar of F has a finite subcobar. First of all, let us consider the case that F is not closed and bounded interval on AB. AB is the closed. Let curly F be an open cobar of AB. Define it to be the set of numbers. Now, first of all, what will be the open cobar? Open cobar of a set. We have to discuss this definition first. This is the definition. A set curly O of a real number is called open, provided for each x belongs to O, there is a R greater than 0 for which the interval x minus R, x plus R contained in O. So this is the actually definition of open sets. And countable set and uncountable set. So a finite set is called actually countable and infinite set is called uncountable. So we have to remember this. So the open and closed set, we can define open and closed set in this way also. Even A belongs to R and epsilon greater than 0. The epsilon neighborhood of A is the set this. And an open set O is open. If for every A belongs to O, there is an epsilon neighborhood. A belongs to V. V is the also ball. with radius epsilon and center A, which contained in O. So this is the also definition of open and closed sets. Union intersection of open sets can be written as like this. Let O lambda, lambda belongs to A, be any collection of open sets, then all union of epsilon belongs to A will of O lambda is open. And this is the also a finite collection of open sets with intersection. This is also definition of limit point. We have discussed the whole ball. B is the ball of X with radius epsilon will be intersection with A, then contains some point A with A doesn't belongs to X. It is called limit point. The limit, a point X is a limit point of a set A if for all epsilon greater than 0, the intersection of open ball of X with radius epsilon with center X with A contains some point A belongs to A which is not equal to A is not equal to X. This is the actually, and some terminology the author uses limit point equals to cluster point or accumulation point. And this is the example. A equals to 1 by 1, 1 by 2, 1 by 3 dot dot. No point of A is a limit point of A, but 0 is a limit point of A, because 1 by n tends to infinity, then we get easily 0. Number 2, B 0.01 closed interval. The point X is a limit point of B because X belongs to B. This is a theorem, important theorem. A point X is a limit point of a set A if and only if X equals to limit of n for some sequence n contained in A satisfying n is not equal to X for all small n belongs to natural number. So this is the proof. This is left for you. Very easy proof. Now, what is the isolated point? A point A belongs to A is an isolated point of A if it is not a limit point of A. Okay. For example, capital A is the union of -1, 0 and 1/2, 1 by 3, 1 by 4, etc. series. If -1 less equal to X less equal to 0, then X is a limit point of A. If X equals to 1 by n for some n belongs to capital N, then X is an isolated point, because for n tends to infinity, it will become 0. This is why isolated point. Now, similarly, definition of closed in case of limit point, F set F is closed if it contains all of its limit point. Now, closed interval can be defined as every closed interval CD can be written as X belongs to R, where C X lies between C and D. C less equal to X, X less equal to D. For example, the limit point of rational number Q. What is the limit point of the rational number? Real number. If X belongs to real number, any real number for epsilon greater than 0, this is the neighborhood which contained in ball of with center X and radius epsilon, which contains a rational number A with epsilon radius not equal to X. Okay, this is why is the limit point. Now, density of Q in R. For every Y belongs to R, there exists a sequence of rational number converging to Y. So both open and closed. The set R and null or empty set are both open and closed. They are the only subsets of real number with this property. Definition of a closure. What is the closure of a set? Okay, given a set A, which is the subset of real number, let L be the set of all limit points of A. The closure of A can be defined to be closure of A defined as A union all the limit point L. So, for example, closure of rational number will be real numbers. Similarly, closure of the series 1 by n, 1 by 2, 1 by 3, 1 by 4, etc. will be what? 0, 1 by 1, 1 by 2, 1 by 3, 1 by 4, etc. And similarly, closure of open interval AB will be closed interval AB. This is the example of closure of a set. This is another theorem property. A closure of a set is closed and it is the smallest closed set containing A. This is the smallest one. What should the phrase closure of A is the smallest closed set containing A? What do you mean by this? Actually, closure of A is a closed set containing A such that if capital F is any closed set containing A, then we can write A is the subset of closure of A and closure of A is the subset of capital F. Since any intersection of closed sets is closed, if F is the collection of all closed set containing A, then we can write closure of A is the intersection of all F belongs to curly F will be F. So in that case, is the smallest one. Similarly, the interior of a set A. Interior of a set is also the largest open sets. The closure of a is closed, it is the smallest closed set containing A. This is the proof left for you. Now the definition of the complement of a set. There is a proof also. And this is the De Morgan's law. You must know complement. Union of all complement will be intersection, the individual complement. And the complement of intersection of all finite elements of E will be the union of individual complement of their union. This is the proof of De Morgan's law. You must know from the intermediate section. So union and intersection can be written as for closed set. And this is the theorem. Infinite intersection of closed set. This is the example. Now, what's the actually definition of interior? That is the subset of real number. The interior of E denoted by E naught is the set can be defined as X belongs to E. There exists a ball with center X and radius epsilon which contained in E. In that case, this is called interior of a set. For example, the interior of a closed unit disk in 2 dimension, xy belongs to R square, the circle, inequality circle, x square plus y square less equal to 1 with radius 1 and 0, 0. Is the open unit disk, and this is the open and the upper one is closed. So this is the actually interior. Right. For example, interior of real number will be the real number. Interior of rational number will be empty. Interior of closed interval AB will be open interval. And interior of the series 0, 1 by 2, 1 by 3, 1 by 4, etc. will be empty. There are closure of an interior to theorem. We can prove it easily. Now the compact sets, the 3 most important kinds of sets in analysis, 3 most important kinds of subsets of R in elementary real analysis are open sets, closed sets, and compact sets. So open sets and closed sets we discussed in earlier. Now what will be the compact sets? Okay, A is the set, a set K, which is subset of real number, is compact if every sequence in K contains a convergent subsequence whose limit belongs to K. So there will be a limit which will be contained in K, and every sequence in K will be contains a convergence subsequence whose limit belongs to K. Then in that case, this K will be called compact. For example, n is a sequence of an arbitrary sequence is the in the closed interval 0, 1. Since this sequence is bounded, so by the we have discussed Bolzano-Wierstrass theorem. By the Bolzano-Wierstrass theorem, we observe that there is a convergence subsequence. Its limit will belongs to what 0, 1. So 0, 1 is a compact set. This is the actual application of Bolzano-Wierstrass theorem we have discussed in earlier. The definition of bounded set. A set A of real number is bounded if there exists some capital M greater than 0 such that absolute value of modulus of x less than M for all x belongs to A. Okay. This is in that case, it's called bounded set. There is a theorem about the compact set. A set K is, which is subset of real number compact if and only if K is both closed and bounded. So we can prove it easily. Now nested set, compact set, nested. If K1 is the superset of K2, is the superset of K3, is the superset of K4, etc., is a nested sequence of non-empty compact sets, then the intersection of all can will be non-empty. We can prove this theorem by using the above definitions. Now Cantor set, the Cantor set is a compact. Now what will be the open cobar? Definition of open cobar. Let A is the any set which is subset of R. An open cobar of A is possible in finite collection of open sets O lambda, where lambda belongs to A, such that A can be written as the subset of all union of O lambda. Given a set of cobar A, finite cobar is a finite subcollection O lambda 1, O lambda 2, dot dot O lambda n. This set as of sets of the original cobar such that A is the subset of union of all collection of cobars O lambda 1, O lambda 2, etc. For example, 0, 1 minus half such that small n belongs to capital N and n greater or equal to 2. Because if we put 1, this will be 0, 0. This is why we are considering n greater or equal to 2 is an open cobar of the open set 0, 1. Okay. If we put n greater or equal to 2, then all the points lies in 0, 1, which does not have a finite subcover. So this is the open set which has no finite subcover. This is now Heine-Borel theorem. Let K be a subset of R. The following three statements are logically equivalent. K is compact, K is closed and bounded, and every open cover of K has a finite subcover. This is actually Heine-Borel theorem, very important theorem. It is not sufficient to find some open cover that has a finite subcover. There must exist a finite subcover for every open cover of K. We have to remember this concept. Now the equivalence of first two statement has already been established. Now we will discuss. Suppose K is closed and the equivalence of that means K is compact and K is closed and bounded. We have discussed in previous theorem, closed and compact. K is closed and K is compact. Okay. So first one, assuming K is compact, we'll show that K is closed and bounded. First, we'll show K is bounded. Suppose by the way of contradiction, suppose K is not bounded, then there exists X1 belongs to K with the absolute value will be greater than 1. There exists X2 belongs to K, also X2 absolute value of X2 greater than 2. And in general, there exists Xn belongs to K with Xn absolute value greater than n. If Xn K is the subsequence of Xn whatsoever, then the subsequence will be absolute value of subsequence will be greater than nk greater or equal to k, which is unbounded and hence does not converge. This contradicts the fact that every sequence in a compact set contains some convergent subsequence that converges to a limit in k. Therefore, k is bounded because it has a limit point. Okay, this is why it must be bounded. Next, we will show that k is closed. Let xn be a convergent subsequence as convergence sequence in K with X. Limit of Xn will be X. This is converges to X. We must show that X will be the element of K. By the definition of compactness, there is some convergent subsequence X and K that converges to a point in K. But every subsequence of the convergent sequence converges to the same limit point as the limit of Xn is Xn. So X belongs to K. This shows that K is closed. It has a limit, same limit. This is why it is closed. So we have shown that if K is compact, then K is both bounded and closed. Now conversely, assume K is closed and bounded. Since K is bounded, the Bolzano-Wierstrass theorem tells us that any sequence in K has a convergent subsequence. This convergent subsequence to a point in K, since K is closed, hence K is compact. Although the compact are not necessarily intervals or the union of intervals, many theorems about closed intervals are true if the phrase closed intervals is replaced by the compact sets. So now we'll discuss the Heine-Borel theorem. Heine-Borel theorem. So we have already proved that K is compact, K is closed and bounded. Now we'll show every open cover of K has a finite subcover. So the equivalence of two statements has already been established. Now if K is closed and bounded, let O lambda belongs to A has be a collection of open sets that covers K. We used to show that there exists a finite subcover. Suppose by the way of contradiction that K does not have a finite subcover, let I not be a finite closed interval containing the compact set K. Bisect I not into two halves A1 and B1. If both A1 intersection K and A2 intersection K have finite covers from the sets O lambda belongs to A, then K has a finite cover. But we have assumed that K does not have a finite subcover. So if K intersection A1 does not have finite subcover, set I1 equals to A1. Otherwise, K intersection B1 does not have finite subcover, and we set I1 equals to B1. Similarly, we bisect I1 into two subintervals A2 and B2. If K intersection A2 does not have finite subcover, we set I2 equals to A2. Otherwise, K intersection B2 does not have finite subcover. So we set I2 equals to B2. Continuing in this process, we obtain a nested sequence of closed interval as follows. The I0 is the nested to I1, I1 nested to I2, and I2 nested to I3. That means I1 is the superset of I1, so I1 is the superset of I2, I2 is the superset of I3 in this way, such that K intersection IN. IN means what? I0, I1, I2, I3 dot dot. So K intersection IN has no finite subcover for all n belongs to n. Since the interval IN plus 1 was obtained by bisecting IN, so we have the limit of IN will be 0. For each n, K intersection IN is a non-empty compact set, then the intersection of the nested sequence of compact sets is non-empty. So intersection of all these intersection set will be non-empty. Let X is an element which contains in this nested intersection. Then X belongs to In for all X. So let X will be the element in In. Then X is the belongs to K intersection In, and this In limit In tends to 0, then converges to 0. It follows that all intersection of K intersection In will be X. Then there must exist some O alpha naught such that X belongs to alpha naught, but there is an N such that small n greater or equal to N. So X is the element of K intersection In, which is the subset of O subcover O lambda naught, which contradicts the fact that K intersection In does not have a subcover. But there is a contradiction we considered in earlier. K intersection In does not have a finite subcover. This proves that if K both closed and bounded, then every cover of K has a finite subcover from 3 to 2. That means if it is a finite subcover, then it will be bounded. Assume that K is a set of having the property that for every open cover U lambda belongs to A, there is a finite subcover K. We must show that K has both bounded and closed. For each X belongs to K, consider the open neighborhood B1 and open neighborhood. This is the actually open ball of with center X and radius 1. So this ball such that X belongs to K is an open cover of K which has a finite subcover B1, B2 dot Bn, B1 Xn for some X1, X2 dot Xn, which are the element of K. Since K is contained in the finite union of bounded sets, K is bounded. Now to show the K is closed, we must show that if Yn is a Cauchy sequence in K, then we must know that limit of Yk sequence equals to Y belongs to K. Suppose by the contradiction that Y doesn't belongs to K, we construct an open cover of K for every X belongs to K. Let Ox be the interval of radius X minus Y, modulus of X minus Y divided by 2, centered at X. Then the open cover of O of the point X such that X belongs to X is an open cover of K. By the hypothesis, there exists a finite subcover Ox1, X2 dot Oxn. Then the set epsilon naught will be the minimum of the distance xi and y divided by 2 such that I lies between 1 and n. That means a closed interval with 1 comma n. Because limit of yn equals to y, there is some n large enough such that yn minus y less than epsilon naught. But then this yn does not belongs to the subcover of Oxy. Thus, the subcover does not contain the points in Yn. It is a contradiction. This proves that K is both closed and bounded, which completes the proof of the theorem. This is actually a complete proof of theorem, which is very famous theorem, Heine-Borel theorem. So I hope if you do practice more, you can write easily. Now another proof of Heine-Borel theorem. The statement is let F be a closed and bounded set of real numbers, then every open cover of F has a finite subcover. Proof, let us first consider in that case F is closed and bounded interval AB. Let curly F be an open cover of AB. Define E be the set of numbers X belongs to AB with the property that the interval AX can be covered by a finite number of sets curly F. Since A is the element which belongs to A, E, and E is non-empty, since E is bounded above by B by the completeness of real number, so E has a supremum. So define this supremum equals to C. Since C belongs to AB, there is an O belongs to F that contains C. Since O is open
there is an because there is an epsilon greater than 0 which is very small, and such that the interval c minus epsilon c plus epsilon is contained in O. Now c minus epsilon is not an upper bound for E, so there must be an x belongs to E with x greater than c minus epsilon. Since x belongs to E, there is a finite collection 1 O2 dot dot OK of sets in curly F that covers x. Consequently, a finite collection 1 O2 dot dot OK comma O covers the interval A C plus epsilon. Thus C equals to B for otherwise C less than B, and C is not an upper bound for E. Thus, closed interval can covered by a finite number of sets from curly F, proving our special case. Now let F be a closed and bounded sets and F an open cover of capital F. Since capital F is bounded, it is contained in some closed bounded interval AB. In this proceeding, proposition tells us that U equals to real number converts to F is open since F is closed. Let F star be the collection of open sets obtained by adding O to F. That is F star equals to what? F union O. Since F covers F and F star covers the closed interval AB, so by the case just considered, there are a finite subcollection of F star that covers AB. Hence F, capital F. By removing O from the finite subcover of F, if O belongs to the finite subcover, so we have a finite subcollection of sets in F that covers F. We say that a countable collection of sets En, these sets will be n equals to 1 to infinity is descending or nested, provided En plus 1 is the subset of En for every natural number n. It is said to be the ascending providing for every natural number. So this will be descending if this, and the ascending will be this. So in this case, this is the actually proof of Heine-Borel theorem. So this is the complete proof of another proof of Heine-Borel theorem. Okay, now what is Cantor set? In our previous lecture, we have discussed about the open sets, closed sets, and compact sets. Now we will discuss about the concept of Cantor set. The Cantor set will be a very curious example of compact set. Understanding it will help us avoid a certain possible misconception about compact sets while depending our understanding of compact sets. First, we will define the Cantor set. Let C naught equals to the closed interval 0, 1 with the closed interval from 0 to 1. Define C1 another interval by removing the middle third of an interval as follows. Middle third of an interval. C naught difference deleting the open interval 1 by 3 and 2 by 3, which lies between 0 and 1. Okay. Now this can be written as our closed interval 0, 1 by 3 union 2 by 3 closed interval 1. So define C2 as the set obtained by removing the middle third of the two intervals whose union forms C1 as follows. So C2 can be written as what? 1 by 9, 0, 1 by 9, union 2 by 9, 1 by 3. Union what will be? 2. That means we are taking two closed interval from this closed interval and another two closed interval from this interval. That means between 0 and 1 by 3, we are taking 1 by 9, 2 by 9. And between 2 by 3, 1, we are taking 2 by 3, 7 by 9 and 8 by 9. Okay. 7 by 9 and 8 by 9 lies in this closed interval. 1 by 9 and 2 by 9 lies in this closed interval. So C2 can be written as like this. In general, having the constructed Cn minus 1 as the union of 2 to the power n minus 1 closed intervals of the length 1 by 3 to the power n minus 1. Okay. And so we form Cn by removing the middle third of each interval to the obtain Cn as the union of 2 to the power n closed intervals of the length 1 by 3 to the power n. Observe that have a nested sequence like this. C naught is the superset C1, C2, the superset C3, dot dot. So C naught is the closed interval 0 to 1, 0 to 1, and C1 we are making two closed intervals 0 1 by 3 and 2 by 3 1, and C2 also C2 forming with 0 1 by 3 closed interval. We are taking another two closed interval 0 1 by 9 2 by 9 1 by 3. So there are also 2 by 3 1. In this closed interval we are taking another closed interval 2 by 3 7 by 9 8 by 9 1. So proceeding in this way, we get the next nested sequence of sets. Now definition of Cantor middle third sets. The Cantor set of the set C defined by C equals to what will be intersection of all collection of Cn, where n equals to 0 to infinity. Now length of the Cantor set what will be? Cn consists of 2 to the power n intervals. If C equals to 0, C naught, then 2 to the power 0, that means one interval, one closed interval. If n equals to 1, then means C1 consists of 2 to the power 1, that means two closed interval. So we are considering this C naught. If n equals to 0, then one closed interval. If n equals to 1, then two closed interval. That means 2 to the power 1. If n equals to 2, then 2 to the power 2. That means 4 closed interval. So in this way, if n equals to, the length will be what? Interval length will be 1 by 3 to the power n. Because if n equals to 0, then one closed interval. So 1 by 3 to the power 0 means what? 1 by 1. That means length will be 1. So if n equals to 1, if n equals to 1, then 2 to the power 1. That means two closed interval. So 1 by 3 to the power 1. That means length will be 1 by 3. How length will be 1 by 3? Actually, C1 length 1 by 3. 1 by 3. This length what will be? 1 by 3. Similarly, if n equals to 2, the length will be what? 1 by 3 square. That means 1 by 9. This length what? 1 by 9. This length also 1 by 9. This length what? This subtraction 1 by 9. This subtraction also 1 by 9. So in this way, we can define the length of the Cantor sets. So adding this length gives 2 by 3 whole to the power n. But 2 to the power n by 3 to the power n, if we take multiplication of this, we get 2 by 3. So which tends to 0 as n infinity. It seems like C is a very small set. In a more advanced and analysis course, we would study measurable sets. The Cantor set has Lebesgue measures 0. However, in terms of cardinality of C equals to cardinality of real number. To understand the Cantor set, it is very useful to understand the base 3 representation. Now, decimal in base B, where B greater or equal to 2 and B is the belongs to real number. Decimal in base B, where B belongs to natural number, this is 0, 1, 2 up to B minus 1. In base 10, we can write this one. In base 2, this is the binary. And base 3, we can write like this. So if B greater or equal to 3, the base can be written as A equals to B minus 1. Okay. The last formula just is a geometric series. A by B square, A by B cube, and this means all equals to 1. So in the construction of Cn, we obtained Cn as the union of 2 to the power n closed intervals, and each length of what? 1 by 3 to the power n. Now let Ln denote the set of length endpoints of the closed interval whose union forms Cn. If n equals to 0, then length 0. If L equals to 1, then length will be the closed interval 0, 2 by 3, and L2 this. In this way, we get the series. Actually, this is the geometric series. Now, very important theorem on cardinality of a Cantor set. Cardinality of C equals to cardinality of real number. Since C is the subset of the closed interval Z1, so we have cardinality of C less equal to 0, 1, absolute value of this interval, that means real number. On the other hand, write each element of the open interval 0, 1 in base 2. So if we write in base 2, 0, a1, a2, dot, a3, dot, dot, where each n belongs to closed interval 0, 1. And we avoid any representation with infinitely many repeated ones. Define the function z from open interval to C by this. This is the z function and base 2 and this base 3. So Bn can be represented as 0 if n equals to 0 and Bn equals to 2 if n equals to 1. Thus mapping is an injection. Injection means what? 1, 1. So cardinal of real number will be the modulus of the open interval, that means length, less equal to cardinality of C. Since cardinality of C is less equal to cardinality of real number and cardinality real number is also less equal to C, so by Schrodinger-Bernstein theorem tells us that these are two sets are equal. Now, a very interesting exercise. If C is the set Cantor set, then prove that C plus C equals to 0 to closed interval. Now, x plus y equals to s must intersect C1. This the two sets in cross product. This is the x-axis 1 by 3, 2 by 3, 1 and 2. This is the 0, 0 to interval. Similarly, 0 to. Now, if we take the x plus y, and this is the square with length 1 by 3, and this is also length 1 by 3, this also 1 by length 1 by 3, and this is also length 1 by 3. So we can easily prove that the C plus C equals lies between the closed interval. So we can visualize with the graph this each length is 1 by 3 square. Now fix S is the subset of closed interval 0 to, you want to find x1 y1 which is belongs to C1 such that x1 plus y1 equals to S. We know that C1 can be divided into two open interval taking 1 by 3 and 2 by 3 inside the 0 2. Then we have that this plus this equals to same 0 2 by 3, and similarly this sum will be this and this sum will be this. Hence C1 plus C1 equals to what? All union. All union equals to actually 0 2. So far any S belongs to 0 2, we can find x1 y1 belongs to C1 such that x1 plus y1 is equals to S. So from this graph we analytically we can prove this also. Now a convenient way to visualize this result in xy plane to shade the four squares corresponding to the components of C1 cross C1. So we observe that for each S belongs to 0 to open interval, sorry, closed interval, the line x plus y equals to S must intersect at least one of the squares. That means this line intersects one of the square. Okay, this line, 1 point. 3 squares will be intersects. For each n, we can draw a similar picture with intersecting number of smaller square. Our job is to argue that the line x plus y equals to S continues to intersect at least one of the smaller squares. To argue by induction, suppose that we can find x and y1 belongs to C1 such that x and y1 equals to S. To show that this must hold for n plus 1, let's focus attention on square from the nth stage where x and y1, xn plus y1 equals to S holds. where x plus y equals to s intercept nth stage square. Moving to the n plus 1th stage means removing the open middle third is shaded region, but this result in a situation precisely like the one in the above figure. So implying that the lines must intersect n plus 1th stage square. This shows that if there exists xn plus 1, yn plus 1 belongs to cn plus 1, where the line xn plus 1 plus yn plus 1 equals to s. So in this case, we can also show this result, okay, by mathematical induction. By using Bolzano-Wierstrass theorem, convergence where exists a convergence subsequence, we can also and prove that these relations. So this is very interesting exercise. The C is the Cantor set. We can prove C plus C equals to 0, 2. Now the Cantor set is compact. In the definition of the Cantor set, each Cn is the union of 2 to the power n closed interval. 2 to the power n closed intervals of length 1 by 3 to the power n in the interval 0, 1. So Cn is compact. By the definition of Cn, we have nesting C1, C0 superset of C1, C1 superset in this way. Hence, the intersection is closed and bounded and hence compact. But by the nested compact property, we can write C equals to intersection of all Cn, which is non-empty. So we can say that the Cantor set is compact. So in this class, we have discussed actually what is real analysis and concepts of sets and concepts of field also, and supremum, infimum, neighborhood of limiting point, sequence and series, and at last Heine-Borel theorem, Bolzano-Wierstrass theorem, and Cantor set theorem. So thanks to everybody and best wishes.